So, hello everyone. I hope now it works also in the presentation mode.
It worked perfect. Thanks.
Perfect. I'm happy. So yeah, thank you, Professor Kurtuluş, for hosting the session, and thank you, Mr. Alba-Baba, for inviting me to this talk. I hope everyone is healthy, and it's a pity that we don't see each other in present or real. And many thanks for the nice talks so far. It was very interesting. And also a warm welcome from my side. I'm very honored to present a study on behalf of my colleagues. So now, I'm sorry. Yeah, so just maybe I will present myself shortly. I'm Dorothee Siefert, so I'm a PhD student at the moment at Karlsruhe Institute of Technology in Germany. And I also work as a project manager at the energy company EnBW, located in southern Germany. So, what is this study about? It was recently published in the Turkish Journal of Earth Sciences. Thank you very much. So, during a geothermal exploration campaign of the joint venture Borusan and BW Energy, an approximately 3,900 meter deep well was drilled. It was, it was called GP-1. So, and to determine following drilling locations, it was aimed to get a better understanding of the geologic structures in the vicinity, the local vicinity. And as reported in literature, we wanted to try to allocate the two drilled marble horizons of GP-1 to surface analogs, so which are typically the reservoirs or part of the reservoirs in that region, together with gneiss and schist intercalations. I think everyone or a lot of you know, so I don't tell anything new there. And therefore, according to the literature, we searched for comparable outcrop locations of the two different marble horizons known in the area. To be able to stratigraphically define the geological unit of the drilled marble sections in the well, and to compare the cuttings of the well and the surface analogs, we chose different petrographical and geochemical methods, also suggested by literature, and we determined different parameters such as color, light transmission, maximum grain size of the carbonates, and of course the major and trace geochemistry, and also rare earth elements. As well, we did rubidium and strontium geochronology. We hope to gain a better tectonic stratigraphic understanding by our study, so to get a benefit for geothermal exploration by improving the definition of the reservoir graben geometry in the graben there. So, but as the marble composition is controlled by a lot of processes, so the composition of the limestone precursor, and this is a challenge, and therefore we chose this multi-proxy approach, and it's definitely needed. So just quickly about the regional geology and the study area. I think the most of you are quite familiar and know even better about the geology, so I just try to go quickly over it. We are in the region of the Menderes Massif, which is cross-cut by three roughly east-west striking graben systems into these three submassifs. And the Neogene Büyük Menderes Graben separates the central and the southern Menderes Massif, and the graben systems were already described, I don't remember by whom, as a result of a basin and range-like extension of Neogene age. And in the graben system, the geological units are divided into different compartments by antithetic faults. So the neogene sedimentary cover consists of breccia, conglomerates, melisandstone marls, and claystones. And below we have Pliocene formation, which represents the earliest continental to lacustrine deposit above the basement. And then the basement, according to the NAP stacking model in the region, we have 4 naps, and they are named Bayindir. I'm sorry for the pronunciation, Bostak, Schiene, and Selimir. So from bottom to top. And the Bayindir, according to literature, consists predominantly of phyllite quartzite marble and cretaceous, so indicating a lower metamorphic rate compared to the other. And the Bostak nap comprises mainly metapelite and granite, metagranite, with sometimes also eclogite and amphibolite intercalations. And the Schiene nap consists mainly of orthogneiss in that area, metagranite and pelitic gneiss also. And the Selimir nap is subdivided into a lower section of metapelite and weakly deformed metagranite, and the upper part composed of also metapelite and marble. And the filling of the Büyük Menderes Graben consists of the neogene to quaternary sedimentary rocks, as I already told, and the Graben shoulder comprises the metamorphic sequence as just described. So in the northern part, we have the Cretaceous marble, which is present along with the Paleozoic marble horizon, and further north, a large area can be seen on the right figure is covered by the Precambrian gneiss and schist. So the analog stratigraphy is represented in the southern part of the rift system, but the Cretaceous marbles are not present there. So the detailed figure on the right, shows everything in detail. So the GP-1 well here, and the outcrop areas with marble indicated with the black dot in the northern escarpment and in south as well. So the samples from the southern escarpment are indicated with Paleozoic, and from the northern escarpment with Cretaceous based on the mapped geological formation. The cutting samples from the GP-1 well are differentiated in shallow, in the depth interval from 1,050 meters to 1,325 meters, and the deep marble bearing horizon based on the intersection in the well in the interval from 3,600 approximately to 3,870 meters. So about the general procedure and the methods. So in total, we have 17 marble surface and cutting samples, which were analyzed by the different petrographical and geochemical methods. The cuttings are taken as usual in 5-meter intervals and were lag time corrected, washed and dried, and on-site investigated by binocular regarding the petrographical features, and then we selected samples within the marble horizons, which were then investigated further with also polarized microscopy. So we took this approach from Rika et al., which was originally called the provenance determination key, modified it a bit. So after sampling, the marbles are classified as pure or impure, calcitic or dolomitic, and here we applied an approach by Rosen, where a pure calcitic marble is characterized by a modal calcite content of higher than 95%, and macroscopic characterization we did of color, rock texture, including shape, preferred orientation, pattern, grain shape, structure, as I said, maximum grain size and grain size distribution of the calcite and dolomite grains. And open or sealed fissures and possible weathering features in the field on the hand specimens of the surface samples. And for the cutting samples, these investigations were carried out using the binocular side, and microscopic features were analyzed at the drilling site, as just mentioned. And we sometimes colored, or we prepared thin sections. We colored these thin sections with to distinguish calcite and dolomite. And the thin section description focused on the rock type, texture of the cuttings, and the pattern of calcite and dolomite. So to be able to distinguish or compare. And for the geochemical analysis, the surface samples were crushed and prepared for ICP-MS and OES. So with this method, we analyzed the major and trace and rare earth elements. So we used the equations on the right to detect potential rare earth anomalies. And then we did carbon and oxygen stable isotopic composition of the marble carbonate minerals. And this was also determined by mass spectrometry. And the carbon isotopic composition is given in the delta notation, 2 different standards, oxygen as well. And to potentially detect the ages of the marbles, we tried to select impure marble samples with a significant amount of muscovitic white mica and or biotite, and also the strontium isotopic composition of pure marble samples was measured. And this was done to determine the age of marble deposition from the seawater, and the measurements were done using also a mass spectrometer. So to quickly go over the petrographical results, I do not want to go in very detail here, but this can be seen in the publication as well. But we try to follow the procedure by Rika, as I presented this already, and therefore analyzed the hand specimens regarding main features, as already told. And on the left, we see the Paleozoic marble samples or parts of them on the southern outcrop. And the main marble horizon is quite massive, has a fine to medium grain size and mostly evenly distributed grain size, but partly elongated calcite grains. The accessory pyrite explains the sulfuric odor while crushing the rocks, and typical for this marble is the light bluish gray color, a very low light transmission. And the marble is cross-cut by fine carbonate fissures, covered sometimes with iron oxides. And we did some ADX analysis of carbonate grains of this marble, or of both marbles, and this confirmed calcite as the dominant carbonate mineral. And the Cretaceous marble on the right is composed of a white marble. It's predominantly very fine-grained, massive, with also fine fissures, and both mainly composed of calcite. So about the petrography of the GP-1 well, as I said, we drilled 2 marble horizons. Here, I did not present all wells, just the 2 parts of the well, which are interesting. So to go from the depth, bottom hole, we had an orthogneiss with eclogite intercalations. And above this, the deepest carbonate-bearing rock section was sampled and further analyzed. It's a fault-related alteration zone with a significant calcite content. And above, we have a mixed layer of predominantly banded gneiss and orthogneiss. And then the shallow marble horizon in the depth of 1,000 meters to 1,300 meters approximately is located above a fault-related alteration zone with greenish clay. And the marble consists of mainly calcite, also little dolomite with bulged grain boundaries. It can be seen on the right thin sections. It has a bluish to light gray color here and a low to medium light transmission. So compared to the other cutting samples, this marble has the highest calcite content of up to 75 volume%. And yeah, it contains a small amount, less than 5% of quartz and mica. So about the maximum grain size we analyzed, of the calcite and dolomite grains, they are quite small range, and one outlier is the Paleozoic outcrop sample of this T13-2. So here are our samples, and the box plots are the samples of or compared to various marbles in the region, but also in Carrara, for example. So the maximum grain size of the well samples appears to be small compared to the surface samples, but we can observe no systematic difference, and the cutting size is of about 5 millimeters. So this may have influenced, of course, the maximum grain size determination of the well samples. So to quickly go to the geochemistry and to the major oxides, we have a quite high calcium content, until 60% for the outcrop samples dominated by calcium, and the calcium content in the Cretaceous marble lies within the same range, and we cannot differentiate the Cretaceous and the Paleozoic samples of surface. So they show a similar pattern when they are compared in terms of the concentrations of the major elements, and sodium and potassium contents are mostly below the detection limit, as can be seen on the left figure here. And according to major and trace geochemistry, as I said, the surface samples, for example, cannot be distinguished. And the shallow cutting samples here in red on the right figure, they have similar but lower calcium contents compared to the outcrop material. And compared to the deeper section of the well, the shallow samples exhibit higher calcium content. And also here the concentrations of aluminium, iron oxide, and manganese are similar to the outcrop samples of the shallow wells, but the sodium and potassium concentration reach higher concentrations than in the outcrop samples. And the deep samples of the well, they show a major element pattern, which is a bit different, and has in general all cutting samples have higher trace element concentration than the outcrop samples. So to come to the rare earth elements, here they are normalized to the PAAS standard. So and compared to the Cretaceous samples, the Paleozoic samples tend to slightly lower rare earth contents, but in general they lie within the range of the Menderes region according to literature, with a negative cerium and a positive yttrium anomaly. And within Cretaceous sample, also each sample shows a negative cerium and a positive yttrium anomaly. So the well samples show generally higher absolute or also normalized rare earth element values in comparison to the surface samples. But if we compare, in addition, and what is shown on the right figure, the samples of the deep well section and Cretaceous samples exhibit higher gadolinium to lutetium ratios. So this means that the Paleozoics and the shallow well samples have a lower ratio here, which indicates no significant decrease of the heavy rare earth elements. And
Dear Dorothee, you have also 2 minutes, please.
Yeah, I will quickly go over it. Yeah, here is the result of the stable carbon and oxygen isotopes. Here we can see 2 parts allocating the Paleozoic and shallow well samples for one group regarding the ranges of oxygen and carbon isotope, and similarly the Cretaceous and the deep well samples can be grouped together. So about the geochronology, I'm not very specialist there, so it was mainly done by my colleague, who was a great support there. We could not analyze all samples because not all marble samples had sufficient mica, but what can be concluded is that we cannot see the deposition ages because of the metamorphic overprint afterwards, and the last metamorphic overprint indicated by this investigation yields ages near 30 million years. And yeah, so to come to the conclusion, we did a synthesis of all investigated properties, so petrographical and geochemical properties, and we could allocate the Paleozoic marble from the south to the shallow well part, and the Cretaceous marble from the north showed major similarities to the deep sample of the well, and also regarding the isotopic signature as shown before. Also here maybe just shortly about the rare earth elements. We could show the we had different cerium anomalies, negative cerium anomalies, which point to a seawater origin, and also with the positive yttrium anomalies indicating a seawater influence. And as the Cretaceous and Paleozoic limestone protoliths formed on the shelf of the Neotethys, they must be marine. So we have that the carbon and oxygen isotopic signatures we measured indicate sometimes a meteoric influence, but this must result from processes that took place during diagenesis or metamorphism. And also, as I said, the geochronology age is clustering around this 30 million years metamorphic age. And so we came to the results of the structure of the Büyük Menderes Graben with this easy simplified schematic here for our well, and that we have these 2 marble horizons allocated to the well. I hope I was not too long now, and want to thank you for
thank you very much, Dorothee, for your very clear and informative presentation. So we can have just one short question if the participation would like to ask. I am just looking. Is there any question?
Maybe I can also have a look.
I have a question, Chairman.
Yes, please, Professor.
Dorothee, it's very interesting data and presentation. I really like it. You have a lot of information there about the seawater composition of the Paleoseas actually during Tethyan. Am I right actually? Especially the cerium negative anomaly and yttrium positive anomaly, they are very, very significant actually. Does it mean that these are the proxy of Paleoseas actually?
I would say so. That's what we concluded. And it's quite pronounced, the cerium negative anomaly, and also sometimes the yttrium anomaly is strong.
You don't see that in the modern sea actually, so it's very interesting. My second question is, do you have any geopressure reservoirs in this area?
So I don't know about the developments at the moment, or about the well as well. So I cannot answer this question.
Because they've gone up to 3,600 meters actually.
Yeah, I mean, we had, I mean, at that time, as far as I remember, yeah, we had quite a high pressure, also some with some CO2, and of course the temperature was quite high in the well. So we had some high wellhead pressure at that time. I don't know at the moment about the project.
It's a very good data you presented actually, and I like your data. So you can extract a lot of things from your data actually.
Very good.
Thank you very much for everybody.
I'm sorry about the time. If there are more questions,
Yeah,
contact me. Yeah.
Yes.
Thank you.
Thank you very much again. So